don't know why it's not recording. Okay. Fine. So we are discussing the infinitesimal Lorentz transformation. Okay. So in the last class we saw that the connected part of Lorentz group, that is proper orthogonal Lorentz transformations. Okay. For that group, one can define an infinitesimal Lorentz transformation. Okay. And so if omega mu nu's are the parameters of the Lorentz transformation, okay, then the fact that the Lorentz transformation leaves the line element invariant, okay, and the fact that these are the infinitesimal Lorentz transformation, okay, leads us to this result. Okay. So omega mu nu equal to minus omega nu mu. So that tells us that there are 6 parameters, okay, which defines Lorentz transformation. Okay. Out of which 3 are boosts in Tx1, Tx2, Tx3 plane. So basically these boosts one can think of, if you insert the hyperbolic functions, then one can think of this as rotation in Txi plane. Okay, Tx1, Tx2, Tx3 plane. So you can say it is a boost or you can say also rotation. Okay, but that rotation is hyperbolic rotation. And other 3 parameters are usual rotations, because this rotation also leaves this line element invariant. Okay, so let us see. So I will write down the Lorentz transformation again. Okay. But here we will use what is known as active version of Lorentz transformation, wherein the point in the space-time is actually moved, not the frame. Okay, one can get back to our result, previously obtained result, by just changing the velocities or by just changing the parameters from theta to minus theta or v to minus v. Okay, so it's not a big deal. So I am discussing now the inverse Lorentz transformation or active Lorentz transformations. Okay, so for the boosts in the x1 direction, okay, we had x prime 0 is equal to gamma x0, okay, plus beta x1. Okay, so I will call this as beta 1 x1. Okay, because there will be 3 velocities, right? Okay, so right now I'm discussing just boost along x1 direction, and x prime 1 will be gamma x0, okay, plus gamma x1 plus gamma x1 plus beta 1 x0, okay, where beta is basically beta 1 means v1 divided by c, and gamma is 1 over square root of 1 minus v square divided by c square. Okay, and x2 x3 remains unchanged, so x2 prime equal to x2 and x3 prime equal to x3. Okay, so this beta 1 basically is the boost along x1 direction. Okay, so that you can write. Okay, but first of all notice that this gamma, okay, is 1 over square root of 1 minus v square over c square, and beta is v by c. Okay, so this v is basically restricted from 0 to c. Okay, so v is basically, or v by c is restricted from v by c is restricted from 0 to 1 basically. V by c factor is restricted from 0 to 1, so it should not, it is equal to for only electromagnetic wave. Okay. Fine. So now we can write this transformation in a condensed form, okay, as x prime 0, okay, equal to cos hyperbolic theta 1, okay, x0 plus sine hyperbolic eta 1 x1 x prime 1 as sine hyperbolic eta 1 x1. We have seen this, but again I'm just writing, so it will be x0 plus cos hyperbolic eta 1 x1. Okay, and x2 x3 remains unchanged. So you can see from this that these are the rotations. You can think this transformation as rotation in hyperbolic rotations. Okay, where this eta 1 is basically tan hyperbolic inverse of v1. Okay, v1 by c. Okay, fine. But there will be eta 2 also. If you consider boost along x2 direction, then there will be eta 2. Similarly, if you consider boost along x3 direction, there will be eta 3. Okay? All those boosts can be written in this form. You can think what kind of hyperbolic rotation should I write for general Lorentz transformation. We know the general Lorentz transformation matrix. From that you can deduce basically the matrix in which can be thought of as a hyperbolic rotation. Okay, good. Okay, so since v by c is restricted from 0 to 1, okay, this eta is restricted from infinity 0 to infinity basically. Okay, since v by c is restricted from 0 to 1 and this is tan hyperbolic inverse, so eta is restricted from 0 to infinity. Okay, this is different than what you have already learned for rotation. Recall, if you consider the active rotation, usual rotation about say z axis, okay, what is the rotation? So your x axis goes to x equal to x y z is equal to cos theta minus sin theta 0 sin theta cos theta 0 and 0 0 1. So this represents the rotation about z axis. So if you rotate about z axis, then the coordinate or component of vector will change like this. But note that here this theta is from 0 to 2 pi. Okay, clear? So as far as rotation in your usual three-dimensional space is concerned, okay, your parameter is bounded. Okay, so the parameter space is bounded in this case. Okay, for usual rotation. While here, okay, if you think this as a rotation, then the point is that the parameter space is not bounded. In other words, these transformations are non-compact, while these transformations are compact. Okay, and that causes the profound difference between this boost and this rotation. Okay, so these Lorentz transformations are non-compact because their parameter space is not bounded. Okay, so in the mathematical language it's called non-compact, while here you have the compact support in the sense that this parameter is bounded between 0 to 2 pi. Okay, this will reflect later on. We'll see how this reflects the fact that the parameter space for Lorentz transformation, the boost is not bounded or is not compact. Okay, fine. So these are our Lorentz transformations. Now let us concentrate on infinitesimal Lorentz transformations. Okay. Let us concentrate on infinitesimal Lorentz transformation. For infinitesimal case, I can expand these functions, right, in Taylor series. Infinitesimal, so these parameters eta 1, okay, can be very continuously. So I can start from eta 1 equal to 0, okay, and I can think I can go to this frame by applying successive Lorentz transformations, successive infinitesimal Lorentz transformations. Okay, so let us consider the infinitesimal version of this. So if I take the infinitesimal version of this, okay, I have to expand these functions. Okay, this cos hyperbolic eta, sin hyperbolic eta. Okay, so if you do that, you will get x prime 0 will be equal to expansion of cos hyperbolic. It will be 1 plus eta 1 square by 2, okay, dot dot dot, okay, x0, okay, plus sin hyperbolic, okay. So eta 1 plus eta 1 cube divided by 3 factorial, okay, dot dot dot, okay, x1, okay. So the leading order, okay, okay, you can say that x prime 0 will be equal to leading order, okay. So that means keep the linear order in x1, eta 1, okay. So it will be 1 times x0, okay. So I'm neglecting this part, I'm neglecting this part, okay, plus eta 1 x1, okay. So this is the infinitesimal change in x0, okay, fine. So this tells us that delta x0, which is difference between x prime 0 minus x1, x prime 0 minus x0, this minus this, okay, will be equal to eta 1 x1. Okay, fine. Remember, this is not, this has nothing to do with the Lorentz index. This is not the Lorentz index as such. Okay, this is just a one parameter. Okay, similarly, your x prime 1, you expand this now, okay, you will get, okay, so you will get eta 1 x0, eta 1 x0, okay, plus x1. Okay, so this is also up to order eta 1 square, and this is also up to order eta 1 square. Okay, so I'm neglecting this part. Okay, so this implies delta x1 is equal to, okay, so it will be x prime 1 minus x1. Okay, this will be equal to eta 1 x0. Okay, fine. So these are the infinitesimal changes in x0 and x1, okay, under the boost. Okay, fine. Now recall that x prime, we have written that x prime mu equal to, for infinitesimal case, x prime mu equal to delta mu nu plus omega mu nu x nu. Okay, why? Because this is basically your infinitesimal Lorentz transformation. Okay, fine. Okay, so from this, your delta x mu is basically omega mu nu x nu. Okay, now you can see what will be delta x0. Delta x0 will be omega 0 0 x0 plus omega 0 1 x1 plus omega 0 2 x2 plus omega 0 3 x3. Okay, now you compare this with this. Okay, what will be omega 0 0? From this, it will be clear that omega 0 0 is 0. Okay, then omega 0 2 equal to omega 0 3, these are also 0. You compare this equation and this equation. Okay. Coefficient of x1 will survive, that is omega 0, 1. So omega 0, 1 will be eta 1. Agree? Okay. So in this notation, your omega 0, 1 is only non-zero. Okay. Rest of the omegas, okay, whose first index is 0 will be zeros. Okay, so omega 0, 0 is 0, omega 0, 2 is 0, omega 0, 3 is 0, and omega 0, 1 is eta 1. Similarly, delta x1, from the transformation of delta x1, okay, you can see that omega 10 will be eta 1, omega 10 will be eta 1, and omega 12 equal to omega 13 equal to yeah, these will be zeros. Okay, and omega 11 is also 0. Okay, so for this particular case where the boost is along x1 direction, okay, these parameters can be fixed. In fact, one can do more general, one can consider more general Lorentz transformation. For those also, one can fix this parameter. So I'm giving you just the example how to fix these parameters. Okay, but this is what we are doing is we are basically going in the reverse way. We know the finite Lorentz transformation. We are considering the infinitesimal version of those, and we are comparing with our this delta x. Okay, fine. In actual case, we should only assume this one. Okay, because we don't know what is finite Lorentz transformations. Okay, in actual case, we should start from this and generate the finite Lorentz transformation. But this is just to emphasize that we are on the correct path. Okay, all these notations are in a are in proper manner. Okay. Okay. So basically, from this, so omega 0, 1 equal to eta 1. Okay. From this, one can deduce that this implies that what is your omega 0, 1 is nothing but eta 0, 0, okay, and omega 0, 1. Okay, where I have raised this index. Okay, so this index is raised. So this can be obtained by eta 0, 0, omega 0, 1. Okay, so this will be equal to eta 0, 0 is 1 times omega 0, 1. Okay, but omega 0, 1 is eta 1. So this implies that omega lower 0, 1 will be eta 1. Okay, clear? And omega 10 is what? Omega 10 is eta 11 omega 10. Okay, but eta 11 is minus. So this equal to minus omega 10. Okay, so this implies that omega 10 is minus of omega upper 1 lower 0. So it will be minus of omega upper 1 lower 0. That will be minus eta 1. Okay, so we know omega lower 0, 1, omega lower 10, and that is consistent with our finding that this omega mu nu is antisymmetric. Okay, and rest in for this particular case, all other parameters are 0. Okay, fine. Okay, good. Okay, good. Okay, any questions so far? Okay. Similarly, we can consider the boost along x2 direction, boost along x3 direction, and from that you will come to know what are these omegas, omega 20, omega 30, etc. Okay. So I know in this expansion, in this expression, I know what are these delta x. Delta x mu's are basically omega mu nu x nu. Okay, and I know, given a Lorentz transformation, I know what are these parameters. Okay. Any question? Fine. Okay. Now recall what happens to rotation. Okay. Suppose if I consider a rotation along z-axis by an angle say phi. Okay. This rotation you can write as cos phi minus sin phi cos phi 0 0 0 0 and 1. Okay. Suppose if I want to write, I will start from phi equal to 0. For phi equal to 0, what is going to happen? This will be just identity, because this will be 0 and this will be 1 1 1. So this will be just identity. So phi equal to 0, Rz of phi equal to 0 is identity matrix. Okay. Now what will be Rz of delta phi? Okay. Rz of delta phi will be, you think this as a Taylor series expansion about phi equal to 0, then that will be Rz at phi equal to 0. Okay, and I will put here plus 1 over I, okay, drz phi by d phi at phi equal to 0. Okay, clear, into delta phi plus order delta phi square terms. What will be d? Now we know this matrix. What will be drz by d phi? Okay, this will be rz of phi equal to 0 is identity. Okay, plus 1 over I. 1 over I is for convenience. Okay, we'll come to know why there is this 1 over I factor. Okay, drz by d phi evaluated phi equal to 0. Okay, so what will be this? This will be a matrix, right? What is that matrix? Okay, this will be sin phi, so it will be 0. Okay, cos phi, so cos phi 0, so it will be minus 1. This will be 1. This will be 0 0 0 0 0 0. So this will be equal to identity minus I. Okay, so I will write this as identity minus I times j. Okay, jz. Okay, I will call this as jz. Let me just, yeah, correct. Okay, and times delta. Is it clear to all? So infinitesimal rotation about z-axis can be written in this form. Okay, where jz is this. Okay. So what can be said about the finite rotation for any finite phi? How can I obtain this?
Infinite times this infinitesimal rotation.
What you do
Delta.
is 1 minus I jz delta phi raised to n. Okay. Right? And you take limit as n tends to infinity and delta phi tends to 0. Okay, this limit, okay, so this will be what? This will be product of these terms, right? Okay, this will be product of n times these terms, and then you will take n tends to infinity. What you will get is the following: you will get e to the power minus I j z delta phi. Okay, because there will be some simplification due to jz. So jz square, jz cube, jz cube will be jz. Okay, jz square will be 1. Okay, fine. So from that you will get the simplification, and you can write this limit as e to the power minus I jz delta y. So any rotation about z axis, okay, so any rotation about z axis can be written as rz delta phi equal to e to the power minus I jz delta phi. And these jz are called generators of rotation about z axis. Okay, fine. Okay, so there should be, it should not be delta phi, it should be phi there. Okay, so this should be phi, because I am taking delta phi tends to 0 and n tends to infinity. Okay. Okay. So any rotation matrix can be obtained if you know Jz, and Jz will be same. Okay, once you obtain Jz for infinitesimal case, this is Jz. Okay, you can use that. So here there is only phi. Okay, you can use that Jz, okay, in this expansion. Okay, so you can exponentiate that Jz. Okay, multiply by phi and exponentiate. So exponentiate Jz phi basically with this I factor. Why I is required? Because usually in quantum mechanics we take rotation to be unitary matrix. Okay. This will be Hermitian. Okay. So this, to make this unitary, we require this factor. But it's not required if you are not dealing with the quantum mechanics. Okay. Clear? Okay. So any rotation can be written, any finite rotation matrix can be written as e to the power minus I jz phi. Okay. Similarly, Rx phi can be written as e to the power minus I jx phi, and Ry phi can be written as e to the power minus I jy phi. Okay, this phi here, phi here could be different. Okay, so I require in this representation, I require just 3 angles, right? Okay, where this jx and jy will be some 3 cross 3 matrices, okay, which can be obtained by uh, following the same procedure. Okay, so I can give you the form for these matrices. Okay, so jx will be so it will be jx will be 0 0 0, okay, 0 0 minus 1, okay, 0 1 0, okay, and jy will be 0 0 1 0 0 0 and minus 1 0 0. Okay, fine. So in general, so you know Rz, Rx, Ry. So general rotation, okay, about any axis, okay, by an angle phi can be written as e to the power minus I n phi n. This is the unit vector n phi dot j. Okay, where n dot j means n1 j1 plus n2 j2 plus n3 j3. Okay, and j1 is Jx, J2 is Jy, and J3 is Jz. Okay, and n is any unit vector in 3D, okay, which has a component n1 x cap plus n2 j cap or y cap plus n3 k cap, so z cap. Okay, clear? So any arbitrary rotation can be written in terms of these generators, and you require three of them, three generators. Three generators are necessary and sufficient to specify a general rotation. Okay. This is the known thing from your quantum mechanics, okay, or even classical mechanics. Okay. Now, similarly, I want to do same analysis for Lorentz transformations. Okay. From the infinitesimal Lorentz transformation, how to generate the finite Lorentz transformation. So I want to write some Lorentz transformation for general omega in this form. Okay. Situation will be slightly complicated here. Okay. So recall what are these? These are the rotations. So in your coordinate space, this will be represented by 3 cross 3 matrix. Okay, because J is 3 cross 3 matrix. So J is 3 cross 3 matrix. You consider a dot product of J with n cap, okay, and exponentiate that. Okay, there will be some properties of J which you know. Okay, knowing that, you can simplify that series. You can exponentiate that and then express in terms of series. Okay, and you can simplify also. Okay, so you can combine, you can expand the series and you can recombine by using the properties of J, and you can write it in nice form, nice 3 cross 3 matrix for Rn cap phi. Maybe probably in group theory course we will see this kind of expression. Okay. Set of these transformations, set of all these transformations form a group, okay, known as SO3, spatial orthogonal group in 3 dimensions, 3 spatial dimensions. Set of all such a transformations. Okay. Now let us focus our attention on Lorentz transformation. So same thing we want to do for Lorentz transformation. Okay. So what I will do first, I will consider the infinitesimal Lorentz transformation where this omega is small. Okay. This we have seen that this can be written as identity minus some part, right? Okay, if you see that this will be, where is that? Yeah. So this will be identity plus or plus omega mu. Okay. Now this I will write in the following way. Okay, let me write this. Okay. So this I will write as a matrix equation. So this will be a 4 cross 4 matrix. Okay. That I will write as identity minus I by 2. This is the convention into omega mu nu j mu nu. And I will tell what is this j mu nu. Okay. This is 4 cross 4 matrix. Okay. This is 4 cross 4 identity matrix. Okay. These are the numbers, right? Okay. Then these will be 4 cross 4 matrices. And I want to determine these matrices. Okay. Why I have written j mu nu? Because it will be in covariant form. Okay. And we know what are these omega mu nu. Okay. We know the property also of omega mu nu. Omega mu nu is minus from omega nu mu. Okay. Because of that property, the j mu nu will also be antisymmetric. So try to understand this J mu nu for each mu and for each nu is 4 cross 4 matrix. These are not numbers. Okay, so for example, you have J00, but you will see that these will be anti-symmetric in mu nu. Okay, so this is just zero matrix, 4 cross 4 zero matrix. Okay, J12, okay, will be a 4 cross 4 matrix. So these are not 1 2 entry of matrix J. You should not read like that. Okay, J12 itself is a 4 cross 4 matrix. Okay, so how many such a matrices will be there? That will be decided by how many independent parameters are there. So there will be 6 independent parameters. So there will be 6 independent matrices. And this tells us that only the antisymmetric part, whatever this J mu nu, only the antisymmetric part of this will contribute to this expression. So we can as well take J mu nu to be antisymmetric. Antisymmetric in mu nu. Okay. Here antisymmetric in mu nu does not mean that this matrix itself is antisymmetric. Tells you that if whatever matrix you get, you'll get minus of that if you flip this 2 and 1. Okay, clear? So this is 4 cross 4 matrix because Lorentz transformation is given by Lorentz transformation on your coordinates will be given by 4 cross 4 matrix. I am looking at its infinitesimal version, so that will be clear from this omega. This is 4 cross 4 matrix, so this must be 4 cross 4 matrix for each mu and for each nu. Because this omega mu nu is antisymmetric in mu nu, okay, this will be antisymmetric in mu nu. Okay, so how many independent matrices I should have? So let us list them out. Okay, so J01, J02, J03. Okay, J00 will be 0. Okay, because if I demand that matrix is equal to minus of that same matrix, then that matrix should be 0 matrix. Okay, so these will be 3. Okay, then I have J12, J1, J2, 3, and J13. Okay, these will be 3. And rest of the thing will be J21, but that is minus of J12. So that is not independent matrix. J23 is minus of J32. That is not independent. Then. And J31 will be minus of J13. So that is also not independent. Okay. So number of independent matrices will be 1, 2, 3, 4, 5, 6. So 6 independent matrices will be there. So here, in the case of rotation, you will see that there will be 3 independent matrices: Jz, Jx, Jy. So these 3 matrices, these 2 and that the first one, they are linearly independent in a sense that no matrices can be written as a linear combination of other 2. Okay. So here also, these matrices are linearly independent. Okay, fine. So there will be 6 linearly independent matrices. Okay, remember this is matrix equation, matrix relation. Okay, so if you want, if someone asks you what is mu nth element entry of this, so normally we write Lorentz transformation lambda mu nu, right? This tells you that mu nth element of Lorentz transformation lambda. Okay, so here what is mu nth entry of this Lorentz transformation? Okay. So mu nth entry of this Lorentz transformation will be mu-nth entry of this matrix. Okay, so I should change here now. So I should use here alpha beta, alpha beta, alpha beta. Okay, so please be careful. These are the matrices J alpha betas. Okay, and now when I take mu-nth entry, then you will be talking about mu-nth entry of particular G alpha beta matrix. So for example, if this there will be sum over alpha beta. Okay, suppose this is alpha equal to 0, beta equal to 1. So omega 0 1 J 0 1. Okay, its mu-nth entry. So J01 will be a matrix. Its mu-nth entry. That will be that together with this delta mu. So mu-nth entry of identity will be delta mu. Okay, this combination will be lambda mu. We demand. We are not yet fixed. What are these? These are unknowns. Okay. So we demand that lambda mu nu equal to 1 minus I by 2 omega alpha beta J alpha beta. Why I am doing this, it will be clear. It is just a complicated way of writing the Lorentz transformation, but that complicated way will be useful. So when this Lorentz transformation acts on certain coordinate x mu, this will go to x prime mu. So this will be equal to x, this thing. Remember, there is a sum over alpha beta here. Okay, mu nu x nu. Okay, clear? So x prime mu will be mu-nth entry of this x nu. So this will give us delta. So what will be the multiplication? Mu-nth entry of identity matrix will be delta mu nu x nu. So that will be just x mu. Okay, minus I by 2 omega alpha beta J alpha beta. Now this mu nu will attach where? Not on this, because these are just numbers. It will attach to this mu-nth entry x nu. So this part will be your delta x mu. Okay, clear? And now we have to give some representation to this. Okay, like here in the rotation case, we know these matrices. And how we know these matrices? Just by explicitly writing down the matrix form of RZ phi and then differentiating and then constructing the Taylor series. Okay, same thing one can do here. Okay, one can start from these transformations. Okay, suppose the boost along x1 axis. Okay, then start from this, write it in a matrix form, and then consider the differentiation with respect to eta 1. Okay, and do that and obtain the matrix form of that. Okay? But there is a simpler way, or it's simple, but at first time it's slightly difficult to understand. But let us follow that way. Okay, so this is delta x mu, this part, together with this minus sign. Is this clear till this point? Till this point, everything is clear?
Sir,
Ah.
sir, this omega mu nu is a 4 by 4 matrix,
No,
right? Each
omega mu is not a matrix. Omega alpha beta represents the parameters. Okay. This is 4 cross 4 matrix. This is just a parameter. You tell me what is alpha, beta. This will be omega 0, 1. So this will be just a number. J01 is not a number. If you want, you can form a omega matrix which is written by this omega 00, omega 01, omega 02, etc. You can do that, but that omega is not appearing here. What is appearing is alpha beta omega. That omega alpha beta for given alpha beta is just a number. For example, here we have seen that this omega 10 is same as omega 01 is same as omega 0, omega lower 01 is eta 1. This is just a number, right? Huh? It's just a real number. So I have collection of 6 real numbers. 3 of them represent boost, 3 of them parameterize rotation. Okay. Now, what is appearing here? These are the parameters and these are the generators. These generators are matrices. Okay, so J alpha beta for given alpha and for given beta represents alpha beta matrix, and this mu nu represent munith entry of that alpha beta matrix. Is this clear?
Yes, sir. Sir,
Hmm? Ah.
yes, sir. Sir, we have already established that omega is antisymmetric, omega
Ah.
matrix.
Ah.
Why are
Omega.
we?
So omega is antisymmetric in the following sense. Omega not, don't call this omega as a matrix some kind. Omega 01 is omega minus 0. Omega minus is equal to minus of omega 10. That's it. In that sense, it is antisymmetric. Now go on.
Sir, why are we saying that this J mu nu this should be antisymmetric? Means only 6 independent linear independent components.
Correct. So omega alpha beta is antisymmetric. Suppose this J alpha beta is not antisymmetric. Okay. So J alpha beta, suppose J alpha beta is not antisymmetric. I can write that as a antisymmetric part plus symmetric part. I can always do that. Okay. These are the antisymmetric in alpha beta. So antisymmetric in alpha beta, symmetric in alpha beta gives me 0. So only antisymmetric part in J alpha beta will survive. Agree? Okay. So the antisymmetric part of this will contribute to this. So as well, I can take this to be antisymmetric. Without loss of generality.
Yes, sir.
Okay. So any other part, symmetric part, which can be attached to J will give me 0 contribution because of this. So this combination is important. J alpha beta will not come alone. It will come with the parameters. Like in the rotation generator comes with the parameter phi. Okay. Is it clear? So any infinitesimal Lorentz transformation can be written in this form, where J mu nus represent the matrices. Now I have to give a specific representation to these matrices. Okay. Remember, till now we were discussing the Lorentz transformation on coordinates or your Minkowski space. Okay. So that dictates the size of the matrix. So the size of this matrix is 4 cross 4. Okay, fine. So keep that in mind. Okay. So now I have to give the explicit representation or explicit form for these J alpha beta matrices. Okay, how to give the explicit form? Okay. It's very easy. Okay, so you write down this x prime mu equal to, okay, for infinitesimal case, of course, it will be identity minus I by 2 omega rho sigma j rho sigma. Okay, mu x nu. I have written down earlier, so I am writing it again. Okay, so this will be delta mu nu minus I by 2 omega rho sigma j rho sigma mu nu x nu. Okay, this will be x prime nu. Okay, but on the other hand, your x prime mu equal to, for infinitesimal case, remember our first equation. This will be x mu plus omega mu nu. Okay, omega mu nu x nu. Okay, so you compare this one, these and these are same basically. Okay, so you compare this with this. So omega mu nu must be equal to minus I by 2 omega rho sigma j rho sigma its munith entry. Agree? Because this holds for all x nus. Okay, so this should be x nu here. Then it will become x mu. Okay, fine. So this should happen. So our j rho sigma should be such that if I take its munith entry, okay, and if I contract with omega rho sigma, then I will get omega mu. So here we need to remember that this whatever form of j rho sigma may be, it must be antisymmetric in rho sigma. Okay, so I want to obtain the explicit form for this. Okay, so let us call j rho sigma mu nu, okay, as some object a rho sigma mu nu. Okay, a rho sigma mu nu, and this must be antisymmetric in rho sigma, first two indices. I don't know about this, but this must be antisymmetric in first two, rho sigma. Okay, so what could be its form? And such that if I substitute it here, I will get omega mu. So it's clear that it should be a combination of eta, your matrix, and delta. So you have to, so this must be made up of eta, your matrix, and delta, Kronecker delta. And I have to place index appropriately so that this antisymmetrization is taken into account. So let us see how that can be done. Okay. So I can write, one can think, one can guess it that this form must be I, okay, because then I will cancel and I will get plus sign here. Okay, then how to remove these two? Okay, so I have to adjust, I have to construct a combination of eta and delta. Why delta? Because there is some mixed indices. On eta there are no mixed indices. Eta is either upper mu or lower. Okay, so there are no mixed indices on eta. If it mixed, then it becomes Kronecker delta. Okay, so let me write this as eta rho mu, eta rho. I have taken this index and I will take this mu, okay, and delta sigma nu. Then I will subtract from it eta sigma mu, okay, and then delta rho nu. You can see that this is antisymmetric in rho sigma. You can clear this. Okay, fine. And you see now that if I substitute it here, okay, what I'm going to get? Let us substitute it here and let us see whether we get omega mu or not. Okay. So I times this minus I by 2 omega rho sigma. Okay, so I times eta rho mu delta sigma nu minus eta sigma mu delta rho nu times minus I by 2 minus I by 2 and omega rho sigma. Omega rho sigma. This is equal to I plus sign. So I will get half first term with omega rho sigma. What is going to happen? Eta rho mu delta sigma nu. Okay. So this will be, okay, sigma will be replaced by nu and rho will be raised and it becomes mu. So it will be omega mu nu. Okay. And here I will get minus rho will be replaced by nu and sigma will be raised to upper mu. So it will be omega, but this rho is the first index here, so it will be omega nu mu. Okay, is this clear? But what is this omega? It will be half omega mu nu, so it will be eta let us see, it will be eta mu rho omega rho nu. Okay, omega mu is eta mu rho omega rho nu minus eta mu rho omega nu rho. Okay, clear? But omega nu rho is minus of omega rho nu, so it will become plus here and I will write here omega rho nu. Okay, and this will be, so I can write this will be 2, so this factor of 2 will go, so it will be eta mu rho omega rho nu. This is omega mu nu and this is what we want. Okay, so this combination is actually omega mu nu. So representation of J rho sigma is this now. So munich entry of J rho sigma is this. Okay, so this form is correct. So J rho sigma mu nu will be, so easiest way to remember is that take first index and first index here, okay, and put it on eta. Okay, and rest of the index will be 1 up 1 down, form a chronicle delta out of that. Then from this you have to, you want it will be antisymmetric in rho sigma, so it will be put second index of this and first index here, and then rest of the index should go on chronicle delta and you put I here. That's it. Okay, so this is a representation of generator. Okay, fine. Is it clear? In particular, let us see what happens to J01. Let us find out this. If we know all these entries, we can form 4x4 matrix. Okay, so let us concentrate on J01. So what should be this? This should represent a generator for boost along x1 direction, right? Okay, because this will come up with omega 01. Okay, so I'm concentrating on J01 now and let us see what it gives as a matrix J01. Okay, so J01 mu nu. Okay, what are these entries? Okay, this will be I eta rho is 0, okay, and sigma is 1, so eta 0 mu delta 1 nu minus eta 1 mu delta 0 nu. Okay, so what is this? If eta is 0 here, mu has to be 0. Okay, so non-zero entries will be, okay, what are those? I times mu is 0 and here delta is 1, then mu has to be 1, so 1 1. Okay, minus mu is 0, so this will be out and this will be out. Okay, so I will get this one. Okay, so this is 1, so it will be I. Okay, is it clear? What else is non-zero? If I put mu equal to 1, okay, right, in this term we got non-zero contribution from this term, but I may get non-zero contribution from this term also if I take mu nu properly. So what should be mu nu? Mu nu, if I put 1, then I will get eta 1 1. Okay, so this represents j01 mu equal to 0 and mu equal to 1. And now if I put mu equal to 1 and mu equal to 0, I will get eta 1 1 delta 0 0. Eta 1 1 is minus 1, delta 0 0 is 1, minus 1 it will be plus 1, so it will be 1 again. It will be I. Okay, so this is delta, so it will be j01 1 0. Okay, so in this j01 matrix all the entries are 0 except these ones. Okay, so what should be that matrix? So that matrix is j01 will be equal to 0 j01, so it will be here, this index represents row and this represents column. Row and column. So j01 is I, rest of the entries are 0. Okay, j10 is again I and rest of the entries are 0. Okay, and rest of the entries here also 0 and here also 0. Okay, so let us see what is this transformation. So delta x mu is equal to omega mu nu x nu. Okay, and we also have delta x mu equal to minus I by 2 omega rho sigma j rho sigma mu nu x nu. Okay, so what this represents? Okay, suppose I have the situation where all these omegas are zeros except rho equal to 0, sigma equal to 1. Okay, so let us see what this matrix gives. Okay, delta x mu, okay, equal to minus I by 2 omega 01, okay, j01, its mu nth entry. Okay, so I will write this, I will first expand this and then I will write x nu here. Okay, plus, so it will be minus I by 2 omega 02 j02 plus omega, yeah, so maybe what I will do, I will take this I by 2 common, so let us write it in a fancier way, minus I by 2, okay, omega 01 j01 plus omega 02 j02 plus omega 03 j03. Okay, plus there will be a same combination but with this interchange 10 J10, omega 20 J20, omega 30 J30. So it will become twice actually. So I am not going to write those. Okay. What else will be there? Okay. So omega 12 J12 plus omega 13 J13 plus omega 23 J23, and that's it. Well, if I know this, then other thing will be just twice of this. Clear? Okay, fine. So I'm saying now that all these omegas are 0 except this omega 01 and omega 10 obviously. So I will have similar term right here. Rho and sigma is summed over. Okay, so you have to take all these summations. So it will be 10 J10. Let me write just to avoid confusion. Okay, and that's it. But this term is same as this term because I can replace. I will get minus sign, then I will replace here. I will get one minus sign, so resultantly plus. So this term is same as this term. This term is same as this term. This term is same as this term. Similarly, this will be same as this one. This term is same as this one, etc. So I will get 2. This factor of 2 will cancel. Okay, clear? And so I will left with delta x mu minus I by minus I times omega 01 J01 plus all these things. But I'm saying that all these omegas are zeros. So what remains? So there will be x. So mu nth entry of this. So this entire thing will be a matrix. So you have to take mu nth entry of this and you have to take x nu. So what will be this? It will be minus I omega 01. Okay, J01 mu nu. Okay, x nu. Okay, so J01 mu nu x nu. Okay, so delta x mu equal to minus I omega 01 J01 mu nu x nu. So now what will be delta? Let us fix mu. Let us ask what is delta x0. Delta x0 will be minus I01, okay, J01, okay. Mu has to be 0. If mu has to be 0, then look at this form of the matrix. Then nu has to be 1. Okay. Then nu is 1, x1. What is this? Omega 01. Omega 01 we have already obtained. Omega 01, if I am correct, then it will be minus omega 01 is eta 1. Okay. Omega 01 is so minus I eta 1 J01 and 01th entry. 01 entry will be I. Okay. There will be I here. And then x1. So what will be this? So I times I minus plus, so it will be eta 1 x1. As expected, delta x change in 0th component will be eta 1 x1. This is what is expected, right? See here. Okay, fine. So this transformation, this your Lorentz transformation in the infinitesimal form can be written in this form, where j alpha betas are matrices. Okay, and you can get the form of each and every matrix. So your job is to calculate exercise. Okay, obtain all j mu nu, okay, in the matrix. Okay, so I have obtained J01. So you obtained J02, J03, then J12, J21, sorry, J12, J13, J23. That's it. So you should have 6 matrices. One matrix I have given. Okay, so your job is to evaluate, obtain 5 matrices, rest of the 5 matrices. Okay, is this clear? Hmm? If you have any question, you can ask. I will take 1 minute or 2 minute pause. If you have any question, you can ask. No question? Everything is understood? Hmm?
Yes, sir. This algebra is understandable.
No, not algebra, but is it clear what we are doing actually? Is it
Yes,
clear
sir.
why is it clear why I'm concentrating on only on infinitesimal Lorentz transformations? Why I'm so concerned about infinitesimal form? Can anyone tell me?
We can apply those infinitesimal Lorentz transformation n number of times and obtain
Okay, but see, but the point is that I know the finite Lorentz transformation, right? So what is the point in doing this exercise? You know the complete matrix for Lorentz transformation. I hope that you have obtained that 4 cross 4 general Lorentz transformation matrix. The point why I am writing in this form, I know finite transformation also, right? Why I'm so bothered about this infinitesimal form?
Sir, infinitesimal transformations are invertible. That's why.
Huh? What? No. But any Lorentz transformation, you will have inverse Lorentz transformation, right? So I have your finite Lorentz transformation also invertible.
Sir,
Huh.
for infinitesimal transformations, they are ordered independent.
The infinitesimal Lorentz transformation are order independent. So what? Order independent means?
Means
we
if I
are
have
finding the
three,
generator
three,
of
three
Lorentz
consecutive,
transformation, right?
But so what? Okay, then what? Order independent. What I will do with that?
if I have say 3 or 4 consecutive transformations, so in what order I choose them, it will not means the answer will not depend on that. The final result will not
No,
depend.
that what see what are you saying is that you are extrapolating the analogy for the rotations. Okay. So what you are saying is that if I consider the rotation in infinitesimal form, okay, in the infinitesimal form they commute, and that does not hold at the finite level. Okay, that is separate thing. But why I'm bothered
So we
with
are finding the
it?
generator of the Lorentz transformation, right?
Correct. So the whole point is to determine the minimal set of matrices which generates the Lorentz transformation. Okay, once I know these minimal matrices, okay, I generate the Lorentz transformation. And another use is that, see, you consider the rotation. Okay, as you know, the rotation can be generated by 3 matrices. This J1, J2, J3. see the Sakurai, okay, all these rotations are going to act on what? All these rotation matrices, all these artillery which we build up, they are going to act not only on these coordinates, but on your wave functions. Okay, we are just seeing the coordinates in the space of coordinates. Okay, but actually, what we want to do, we want to act this Lorentz, at least in the case of rotation, we want to act this rotation on the Hilbert space of quantum mechanical states, right? Hmm? So when you solve, say, particle in potential well, three-dimensional potential spherically symmetric well, or hydrogen atom, what you do, you for suppose you obtain a wave function or a state for the system, and you want to check whether what happens to this state under rotation. What you will do, you should have something to act on those wave function, right? Some operator. Okay, and any rotation or any linear transformation in quantum mechanics, apart from the exception of time reversal, are unitary. They are unitary transformations. Okay, so you should be able to write this rotation matrix in a unitary, as a unitary matrix. Okay, and you should know what is the action of this rotation matrix on the wave function. That is known if you know. Now you see, we have written this rotation as e to the power I minus I theta n cap dot j. Why I have written that? You know how j acts on the state space. You know how angular momentum acts. J becomes angular momentum, right? So j, you know how j acts on your state space. Okay. Hence, you know what is the action of rotation on the quantum mechanical Hilbert space. Okay. Your quantum, your three-dimensional space in the rotation in usual three-dimensional space, what you do, suppose you want to see the effect of rotation on some vector, vector in 3D. You will take that so obtained rotation matrix, 3 cross 3 rotation matrix, and you will act on that vector, and you will see another, you will get another vector, right? Correct. But your quantum, no one told you that your quantum mechanical space is three-dimensional coordinate space, right? That quantum mechanical Hilbert space is the abstract space. Okay. In general, it is infinite dimensional space. In hydrogen atom, it is infinite dimensional space, right? You have psi NLM, and n goes from 1, 2, 3, etc. Okay. So how to see this rotation? But you know that under rotation, wave function should transform. Okay, so how to see these rotations? Okay, effect of rotation on those infinite dimensional space, or your quantum, in general, your quantum mechanical state space. Your state space is not your coordinate space. Your state space is different, right? Suppose you want to see what is the effect of rotation on spin. You have a electron, okay, and I want to see how the your spinor, that is plus your suppose the electron is in sz plus state. Okay, so it will be given by column vector 1 0. How under rotation it will transform? But that 1 0 is just a now 2 cross 1 matrix, and how you will act 3 cross 3 matrix on that 2 cross 1 matrix? So there is a clash, right? So you cannot directly use this three-dimensional matrix. But what you need to do is that if you know how J acts, okay, on the states, okay, so you have to construct a J in classical mechanics is given by R cross P. Okay, so you must have some operator which will represent J. and that operator will act on quantum mechanical state space. Okay, but no matter what happens, the rotation effect of rotation on that state space will be e to the power minus I n cap dot the quantum version of J, that is your J hat. Okay, can you understand now? So this is supposed to be done in quantum 2, your Sakurai. This is what your Sakurai tells. This is how your rotation is understood in quantum mechanics. Okay. Now then you say that I want the action of J on the state space. Okay. But there are certain properties of J's. Okay. Jz. So J1, J2, J1, J2, J3, they don't commute among themselves. Okay. But J1 commutes with J square. If they commute, if two operator commutes, then they will have simultaneous eigenspace. So the problem of finding the action on J on the state space reduces to finding the eigenstates of Jz and J square. Okay. Then you introduce, since they commute, okay, then you introduce for quantum number. Okay, and you construct the eigenspace of Jz and J square. Okay, and then you try to express this any state as a linear combination of the eigenstates of J square and Jz. Why? Because on that state, if I do that, then I know how to act rotation on that. Because rotation will be e to the power minus I n cap j cap. And I know how j cap acts on those states. So that is the whole logic. That is why one writes this the effect of transformation as e to the power some generator. That exponential is not important. What is important is the generator part. Because the generator in classical mechanics will smoothly follow to quantum mechanics. It will become the operator. Only thing is that the dimensionality may not be 3. It may be 5, it may be 6, it may be 10. So you should have 10 dimensional representation of that J. So now coming back to the Lorentz transformation, we have here what we have. We have here the 4x4 representation of this rotation matrix of this Lorentz transformation generators. Okay, why? Because I was dealing with the coordinates x mu's. I was acting the Lorentz transformation on these coordinates or coordinate space or any vector v mu in the Minkowski space, physical vector or say classical vector. But if I want to see the effect of Lorentz transformation on some kind of functions which are the solution of certain relativistic equations and which can be thought of as a wave functions. Okay, then I should construct the appropriate representations of these matrices. Okay, clear? So you can understand this by just looking at what happens to rotations. Okay, so these are the rotation matrices. Okay, what they have in common, they commute, they have certain commutation rule. Okay, there will be ijz and jz square with jz with j square commute. Okay, now when you go to quantum mechanics, this becomes the operator. Okay, And then you calculate, if you suppose you consider, you must, I think you know that the eigenstates of these operators J square and Jz is what? Is given by Lm, right? This you know. Okay. For L equal to 1, what is going to happen? For L equal to 1, there will be 3 states. Agree? Okay. Then you take the then you say what is the matrix of Jz in these states. You must have calculated this. Right? Am I correct? Okay. These matrix in 3 dimensions happens to be this one. So if you take Jz, then it will be this one. So yeah, so no, this will not happen. This will not be just this. Just a minute. Yeah, this is the Jz in coordinate representation. Now you calculate this matrix, okay, in these states. Okay, you will get some 3 cross 3 matrix for Jz. Okay, you will similarly you will get some 3 cross 3 matrix for Jx and 3 cross 3 matrix for Jy. These matrices are in general different than this one, this one, this one, this one, because these are just coordinate representations of rotation generators. These are not coordinate representations. These are in the quantum mechanical states. But now you can ask what is the matrix for L equal to 0, right? For L equal to 0, what is your state space? M equal to 0. So it is just a one-dimensional state space. So it will be just a number. There is nothing basically, actually. Angular momentum is 0. L equal to 0 state. Okay. But then you can raise the dimension. L equal to 2. L equal to 2, how many states will be there? There will be 5 states. So you will get a 5 cross 5 representation. Then you have L equal to 6, L equal, etc. So you can have higher dimensional representations of rotation generators. And who decide that what dimensional in what dimension you should work? It is decided by the states. What is your physics? That will decide what representation of this rotation you should look at. Now one can have here, instead of L, one can have here half. Okay. Then you will get 2 cross 2 matrix, right? If it is half, then M is half and minus half. Then you will get 2 cross 2 matrix. But 3-dimensional, you must be thinking that rotation is always represented by 3 cross 3 matrix, right? That rotation has 2 cross 2 representation or 2-dimensional representation on your quantum mechanical state space. Similarly, the rotation will have 5 cross 5 representation on the quantum mechanical state space. Those state space will be L equal to 2. Then you can have, you can talk about the quantum mechanical representation of J for L equal to 3 by 2. Right? And so on. So it's not necessary. So first drop the notion that it is not necessary that for rotation the J is always 3 cross 3. It's not. In the coordinate representation, J is represented by these 3 matrices. That's it. But we are not only interested, as far as classical mechanics is concerned, yes, it is true. We should stop at this level. But in quantum mechanics, we have to look for the action of this rotation on the quantum mechanical state space. That's why we need generalization of this G in appropriate dimensions. So here now you can see here the Lorentz transformation in the coordinate will be given in the coordinate space will be given by 4x4 matrix. Okay, but we don't want to stop at that. We want to go ahead and see what are its representation on certain state space. The topic, this is essentially what is known as the group representations. There will be precise definitions, but this is essentially what is known as group representation theory of group or group representations. So any symmetry operation constitutes a group, okay, and for each group you will have the representations. Okay, so representation is a general, most general thing. Group could be, defining group could be three-dimensional in the sense that matrix or its representation could be three-dimensional or even could be two-dimensional. You can consider rotation in plane. That thing can be represented by this 2x2 matrix, cos, sine, cos. Okay. So rotation in plane is your 2x2 matrix. But you can see its higher dimensional representations still. Okay. So that's why writing a symmetry operator or symmetry transformation in this form is essential. Okay. There are other examples also. It's not restricted to rotation and Lorentz transformation. Obviously, you have translation. You must have seen in quantum mechanics that the translation generator can be written as e to the power I a, which represents translation parameter, dot p, momentum. This is your translation by amount a. Okay. So in the quantum mechanics, these are elevated to operators. P becomes operator. Okay. So your translation is what? Translation means x goes to x prime, vector x prime, which is x plus a. Okay. So from this one can construct a generator for translation. Infinitesimal generator for translation. That turns out to be P. Okay. So it is essential to write any symmetry operation or symmetry transformation in this form, generator form. Okay. And that can be achieved by looking, into infinitesimal Lorentz transformation. So why I'm able to write from infinitesimal to finite? Because the Lorentz proper Lorentz transformations is continuous. Okay. One can start from identity and one can go to any point, any Lorentz transformation from the identity. Discrete Lorentz transformations you cannot do like this. You cannot write generator for that, for discrete case. Okay. Or for other parts like this L plus down, L minus up, those parts you cannot write like this. Okay, so this is only for proper orthogonal Lorentz transformations. So not this one. So the Lorentz transformation, but this one. Okay. So I would again suggest you to go thoroughly with chapter number 3 of Sakurai, Modern Quantum Mechanics. You will understand everything about the rotation. I don't have time to discuss the rotation, okay, but it is required here. Okay, let us continue. Okay, so, okay, do you want break for 5 to 10 minutes? Hello. So, do you want break for 5 to 10 minutes?
Yes, sir.
Okay. So we'll see. I will keep this running, and we'll meet at maybe. So it is 3:10 now. So we'll meet at say 3:20. Okay. Yeah. And we will extend till maybe 1 hour after this.